this webinar for LED Basics, Understanding Lifetime Claims. My name is Robert Tuck. I'm Business Development Director for PhotonStar LED Group. If anyone's got any questions as we go through, there will be a questions and answers session at the end, or feel free to just type questions as we go. We're going to cover all these topics in approximately sort of 20 to 30 minutes for those that are on a tight time schedule. Let's just get these slides started. Okay, so the motivation. Well, within the framework of the 97 Kyoto Climate Protection Agreement, the objective was to reduce emissions in the EU by 2020, 20%, which equates to about 20 million metric tons of CO2 in the professional lighting sector, with a further 24 million metric tons in consumer lighting. So, of course, that's quite a taxing target to meet. And the principal ways of meeting that objective is really by introducing energy efficient sources such as LED, and focusing on the R&D, etc., producing more and more efficient luminaires, but of course banning inefficient ones such as the GLS lamp, and also some sort of discharge light sources such as the low pressure sodium lamp, etc. So that's the principal way that the objectives will be met in the lighting sector. And it's interesting, there was an independent research done by McKinsey & Company just last month, and that said in the professional lighting sector that by 2020, 90% of all lighting in the professional lighting sector will be LED. So I think, like it or loathe it, LED is set to stay, and it's coming as like a tidal wave. So we do really have to try all we can do to accept it. So first of all, I want to talk about equivalent light output. What we're very used to in the past, measuring light actually by watts, which of course is not a good thing, because wattage is indeed power. But of course, we've probably all done it in the past. The lamp goes in the lounge or the living room, and you take the bulb out and it says 60 watts, and you think, actually, when I go down the hardware store and put a new one in, I might want it a bit brighter, so I think I'll go for a 100 watt version. Well, of course, what we're doing there is looking at power consumption, and really what we should be doing is looking at actual emitted light, and light is measured in lumens. So you've probably seen on all the major brands, you know, Philips, Osram lamps, etc. now, when you go into a hardware store, what they're doing is publishing both the wattage consumed and the lumens out on these more sort of energy efficient light sources. So it's educating both the professional and public sector that light is indeed measured in lumens, not watts. So it's now widely accepted that the most useful energy efficient measure is actually luminaire lumens per circuit watt, and that's expressed LM over CW, circuit watts. And we say circuit watts because it has to include any electronics and the losses included in the generation of the light, because generally, whether it be a compact fluorescent lamp that requires a ballast or an LED lamp that requires a driver unit, there are losses in the electronics required to correct the voltage and the currents to the appropriate amount for the light source in hand. So lumens per circuit watt, or luminaire lumens per circuit watt, that's including all losses. That's the way we express efficiency or efficacy. So there's been another sort of a, when you move forward, when you look at lamps, etc., you've got the GLS lamp, which indeed they're measured in lumens, but reflector lamps in the past have been measured in candelas, another unit of measure, because they push the light forward in a very particular cone. You measure light out of a reflector lamp, such as an MR16 or a GU10, in candelas per kilolumen. And of course, that's a pretty tricky thing to understand. So what there's a couple of federations, the Federation of National Manufacturer Association for Lamps and Luminaires in Europe, SELMA, and also the European Lamp Companies Federation, come up with a chart that allows you to compare the brightness of different lamp sources for use in programs such as Dilux and Relux, and also for end users to understand, what brightness a lamp is achieving for the wattage consumed. So if we take the reflector lamp, which is shown bottom left on the slide you're looking at on the screen at the moment, that lamp there is a par 16 on the chart on the right, and if we look at the 50 watt, which is the most popular of lamp of its type, you can see there that it's 300 lumens out. So that gives you a yardstick of measure when you're comparing the light that would be coming out of that lamp at 50 watts, and then maybe comparing it to something such as this fixture here, which is a ceiling star fixture, and I'll be using this fixture, as you can see on the screen there on the right, a number of times for demonstration during this presentation. So you can start comparing the light out for the wattage consumed between different lamp sources, be it a halogen lamp versus an LED, or a halogen lamp versus a compact fluorescent, etc. And most manufacturers actually publish information to assist you with this. So on the screen now we have some slides straight from the PhotonStar catalogue, and you can see there that in the tabulated data we use different light engines, and we class a light engine as the cluster of LEDs mounted on a board, etc., installed into a fixture. So we name these. If you look at the lower section, you can see that the reflector lamp that we've just been talking about, I mentioned a 50 watt MR16 or GU10, and that's actually the Mercury 810 light engine. You can go down, see the illuminance comparable to, which is the top row. It says comparable to a 50 watt GU10. And you can see that the light engine power, the LED equivalent, is only 9.5 watts. That's quite useful because, of course, you've automatically got, again, a measure there against brightness, so you know that enough light is going to come out of one of these fixtures that's going to compare to a 50 watt low voltage lamp or 50 watt mains voltage halogen lamp, but only consume 9.5 watts of energy. You can then see in the chart there the different beam angles that are available in this fixture. These fixtures generally come in a narrow, medium and wide beam. So if we take a typical medium beam, the colour temperature, the most popular version against the halogen lamp is 3000 Kelvin. We can see that it's 663 lumens out for 9.5 watts of energy consumed. Now, most manufacturers of luminaires will actually give you that kind of comparative comparison data. So nice and easy to see what efficiency you're enjoying. So I think we've established there equivalence. We've got two types of LED products that we regularly see offered by manufacturers, etc. PhotonStar generally do full fixtures such as this, but of course many manufacturers are offering lamps, and I thought what we should do is compare the two. They're both LED, and therefore on the face of it would both seem to be very efficient, but why do we have the two, and which one is better? Well, of course we could argue that the retrofit lamp is obviously better in some respects because you take a high energy lamp out and put a low energy lamp in. It's a retrofit, one-to-one, nice and easy, and of course anyone, Joe Public, can do that. Where when you look at a full fixture, of course you've got some electrical connections to do, you will need driver units and so on, and therefore you may obviously need an electrician to put those in, but if you do so, what's the benefit? Well, first of all, longevity. an LED lamp is likely to last about 30,000 hours. You're guaranteed for about warranty for about 3 years. Where when you look at a full fixture from a manufacturer such as PhotonStar, this fixture here will last about we warranty it for 50,000 hours, 5 years on an extended warranty. But it will go on if it's operated according to the install instructions at an average thermal ambient of about 20. This thing will probably likely go on for in excess of 120,000 hours. So life, longevity, is extremely improved when you look at the full fixture. Therefore, because we have all this aluminium on the back to keep the product cool, and that's one thing that's very important, keeping fixtures cool, LEDs cool. We'll talk about that on another slide in a moment. You can see the thermal mass required to keep this product cool versus the little amount of aluminium that's present on this lamp. The warranty, therefore, is going to be vastly improved when you look at the full fixture. We offer a 5-year warranty. Lamps typically are 3 years. Light output, well, of course, when you look at an LED lamp, generally, as you can see here, they've got 3 LEDs in, some have 4. LED fixtures generally have more. We've got the luxury of using more LEDs, therefore we can give better outputs, etc. So lamps, the average at the moment is about 300 to 340 lumens out. This particular one, 310 lumens. The Ceiling Star fixture here, I can get in excess of 900 lumens out. So, of course, a lot brighter. So it's suitable for a much broader range of applications. Colour quality, generally speaking, is going to be better on a full fixture. You can get colour rendering properties. We'll talk about colour in another presentation, but colour quality and colour rendering, how you see and perceive objects rendered under artificial light, is always generally better on a full fixture. Colour rendering on 100 is the best. That's the equivalent of daylight. These lamps typically are 80. These fixtures we can give you in excess of RA90, so you can get better colour quality out of a full fixture. Light distribution, well, the trick with an LED and with a lamp, and we'll talk about this in more detail on another slide, because you have only 3 LEDs in the lamp, you haven't got the luxury of many of them to give you broad beam angles. So generally speaking, they have to drive them harder to get the most light output and deliver it in a very tight cone. So LED lamps are generally between about 20 and 40 degree beam angle. With a full fixture, I can give you beam angles, up to 70 degree beam. So of course, when you're using them in maybe a corridor application, it would be true to say that when you look at the lighting design, because the beam angle is broader, I can use fewer luminaires in an installation than I would if it was just a lamp, because of the broader beam angle. Breadth of range, well, lamps, typically you can get them in 2 different colour temperatures, 3,000, 4,000 Kelvin, and maybe 1 or 2 different beam angles. You may get a non-dimmable and a phase dimming option as well. With this fixture, in this particular range, we've got many different bezel types at PhotonStar. This particular one, 7 beam angles, 4 different colour temperatures, 6 different outputs, 7 different dimming protocols and emergency options as well. So it's a much more flexible design solution for those that are looking to create more interesting lighting designs for their installation. But I think perhaps the most important factor to consider is compliance to regulations. So it could be that you're looking at residential and looking at open sustainable homes. We can give you Code 6 compliance. If you're looking at passive builds, of course, a full fixture like this with a gasket on the back is not going to allow any air bypass, whereas a lamp that goes into a conventional fixture with a bezel with a hole in is air bypass. You could be looking at BREEAM, LEED projects where you've got to be looking at the most efficient products on the market, or could be the the, as I say, co-sustainable homes, or indeed the enhanced capital allowance scheme. All of those I've mentioned look at requiring the most efficient light sources. Co-sustainable homes, I think in excess of 60 luminaire lumens per circuit watt, as indeed is the enhanced capital allowance. Higher light output ratios in excess of 80, and you've got to be looking at 60 luminaire lumens per circuit watt delivered. These will be the fittings that you will need to comply to those very stringent and demanding regulations. Building regulations, if you look at domestic housing, the Part L1A building regulations in the UK, or I think it's posted in Scotland, that looks for 45 luminaire lumens per circuit watt delivered at a minimum of 400 lumens out. Well, if you take the little lamp, this only emits 310 lumens, so it doesn't even meet building regulations. So I think it's true to say you get what you pay for. And if you need compliance, of course, you must be looking at full fixtures. So be it that lamps, they have their purpose. If you're just doing a retrofit in your lounge, of course, it's a nice, easy solution. But if you're looking at compliance, you've got to go full luminaire. A practical example on screen now, I've done a Dialux lighting calculation based on the photometry for the two fixtures we've got here, lamp and a fixture. If you look at the information on the left, the PhotonStar ceiling star luminaire, that scheme is a regular scheme, 4.5 metre square room with a 2.8 metre ceiling height using 9 fixtures. We're achieving 130 lux average. If we go back now to the connected load, we've got 2.73 watts per metre squared per 100 lux. Room looks nice and bright, broad beam angle, etc., and only 9 fixtures. If you look at the lamp, that needs 25 lamps to achieve 102 lux. If you look at the specific connected load, 5.26 watts per metre squared per 100 lux. And in addition, you've got a further 16 wiring points, 16 lots of cable, 16 lots of labour, additional to using a full fixture. So again, a practical example, full fixtures are always better and will give you with a much better looking design. So if luminaires are the way to go, as we've proven, we better look at fixture design and efficiency. Well, for those that have been in design for a long time, like myself, 20 years, we've been looking at electrical lighting. Now, electrical lighting such as fluorescent and discharge lamp sources and halogen lamp sources, not rocket science to be perfectly honest. You get a fluorescent lamp, take a ballast, tricky bit is getting optical control, and then you put it in a pretty housing. It's quite easy to do. When you're looking at LED, however, you're looking at a much more complicated overall system. You have, for example, AC to DC power conversion. That's not the easiest thing to do, and there are the drivers associated with doing that. There's massive variations available, and all the different variants come with different efficiencies. Some with power factors, for example, less than 0.5. Forward voltage efficiencies, LEDs strike at about 2.8 volts. You get forward voltage drift over time. So it's true that when you're looking at these driver units, we need to make sure that we are specifying the appropriate driver for the relevant luminaire to make sure that as the LEDs age, they're still going to strike in the future. Then you've got to be buying the correct LEDs from a reputable manufacturer. White LEDs are generally a phosphor-based blue LED, so you've got to be selecting the right LED. So you've got wavelength conversion efficiencies and phosphor quantum physics here. Then you've got to have optical control. A raw LED without any optic on the front, this is what we call the optic, the plastic lens here, will emit light at about 110, 120 degree beam angle. So you've got to collimate that to get it more usable. Of course, when you put a lump of plastic to collimate the light in front of the LED, you're going to get losses. Then you've got to connect to the mains. Then you've got to have a look at the thermal properties. It's a myth that LEDs don't create heat. They do, but unlike a halogen lamp that radiates heat forward, all the heat goes backwards, which is why we have a large heat sink on the back. That all creates losses. So there's a lot to get right in making an LED fixture. So you need to be making sure that you're dealing with a reputable manufacturer that's going to give you something that is going to be long-lasting and do what you expect it to do. At the end of the day, you got wrong, it's an expensive mistake. So just move on to the next slide. Bear with me. Okay. So design of good LED fixtures. As I've just mentioned, thermal management is absolutely key when you look at the management of the LED itself, and longevity is really quite key, that you keep LEDs cool. They create a lot of heat, but if you don't take that heat away by using a heatsink, they're going to become less efficient and not last very long. Now, both of these fixtures or lamps are designed to be a halogen replacement. And with a full fixture, if you look at the thermal mass of this heatsink on the back, to give you great longevity, 5-year warranty, and probably a life expectancy of, over 100,000 hours, certainly 50,000 hours to a light loss point of about 30%. I need all this aluminium. There's no way when you look at the lamp that I can. This is designed obviously to be a direct replacement for a halogen size in physical envelope, but there's no way I can shoehorn all this thermal mass into something this physical size. So the net result is these things won't last very long. So there's always a compromise. So on the screen, you can see a graph there that shows junction temperature, which is the junction of an LED is the light emitting part, versus light output or relative luminous flux. Now with this fixture, because I have a large heatsink and I actually keep the LEDs running nice and cool by underrunning them with current, the actual junction temperature of the LEDs in this fixture is less than 60. So if I go on the bottom bar there, go to 60, I can see that relative luminous flux as a percentage, I'm going to get about 90% efficiency from this fixture because it's well designed. Where if you looked at something like the lamp, this might have junction temperature way in excess of 100 because we haven't got great thermal management. Well, in excess of 100, you can see that the LEDs would only be about 70% efficient. So keeping these things cool is quite key. There's also another point that one of the leading manufacturers of LED chips, Cree, state is that for every 10 degrees C over 85, the junction temperature goes in their LEDs. For every 10 degrees C increase in junction temperature, your LED efficiency will drop by 3%. But actually, you'll also take a whopping 10,000 hours off life. So again, good design of LED fixtures is key. LEDs, I think it's fair to say, are increasing in efficiency rapidly. We probably see them doubling in, efficiency. Well, certainly in the early days, probably every year they double. It's getting less fast now. However, they do increase, as I say, dramatically. So this particular product was launched in 2008, and we were achieving 40 luminaire lumens per circuit watt. So this fixture, 11.5 watts, delivered 460 lumens. If we look at the same product today, in 2013, this delivers 96 luminaire lumens per circuit watt, 940 lumens out for 9.83 watts consumed. So you can see efficiency is marching ahead at a rapid rate, a great rate of knots. You're always going to be able to cash in on that more readily with a luminaire as opposed to a lamp. Lamps will benefit from this, and indeed, eventually a lamp will probably get to the point where it's over 45 lumens per circuit watt, and critically for building regs, over 400 lumens out. That's what you need, as I say, to reiterate what I mentioned before. Building Regs Part L1A in the UK, you must have a minimum 400 lumens out at a delivered efficiency or efficacy of 45 lumens per circuit watt. Lamps at the moment don't quite get there, but with the increases of efficiency that are coming from the LED chip manufacturers, they will eventually. However, what I would add at that juncture is that the building regs are set to change as well, to keep pushing the boundaries to make sure we meet that Kyoto climate objective. So probably it's likely that just as soon as these reach 400 lumens out and 45 lumens per circuit watt delivered, the building regs will change and will increase, meaning that, again, LED luminaires are still set to be the way forward for quite some time yet. Source numbers can be misleading. What do I mean by that? Well, as I mentioned, if you take any fixture, if you take a bare, on the chart there, you can see a bare GLS lamp or general lighting service lamp. It emits light in all directions. To get delivered efficiency, you need to normally put that in a housing. As soon as you put it in a housing, you get losses. And the losses are expressed as a ratio. So if you take a bare tungsten lamp or a bare halogen lamp, GLS lamp, you get 100% of the light out reaches the space it's lighting. As soon as you put that in a housing, you get losses. So the light output ratio is a ratio between the light emitted as a bare source as opposed to the light emitted when the LED or the lamp or the GLS lamp is put into a housing. And that's expressed as light output ratio. There's two types of lamp or light source. I mean, an LED is a direct light source, so all the light is emitted forward. So you can see there in the bottom picture that an LED, I mean, at the moment we're in excess of 200 lumens per watt chip efficiency in lab. Just as an example here, we've got 100 lumen per watt chip. You put that into a housing such as this, you've got an optic in front of it, you've got losses, so you've got fixture efficiency, driver efficiency, thermal V-rate, etc. That would perhaps deliver 69, 70 luminaire lumens per circuit watt when you've taken into account all the losses. You take the halogen lamp at the top there, the GLS lamp, you've got 17 lumens per watt for the lamp. By the time you take the fixture efficiency, with the fact that it's got a lot of interreflections in the reflector, perhaps only 10 lumens per circuit watt. So that's what we call light output ratio. And therefore it's true to say that the more efficient the luminaire design can be, the more light you'll get out as the ratio of what's initially emitted from the light source or the LED versus what exits the room that you're actually trying to light. So better product design leads to more efficient fittings, means to lower overall system efficiency, so watts per meter squared per 100 lux for the space being lit. It's always better to buy a good designed fitting, a well-designed fitting. So the key to good luminaire design, if you look at this lamp, because it hasn't got many LEDs, but they try and an LED lamp manufacturer will always try and give you the best efficiency rating effectively, and what they do is a little bit of a cheat. You can see on the two polar diagrams there sitting in the center of the screen, you've got a photometry for a typical LED downlight. I think that was a medium beam, probably about 30-40 degree beam angle, versus a lamp. What they might do is give you much more of a torch beam type output, or a very tight beam angle, because what they try and do is deliver the flux up into a very tight cone, take the measurement at the end of the cone on axes in the center of the beam to get the brightest measurement possible. So as I say, this is 310 lumens out in a very tight cone. Well, that's okay if you're trying to light a nightclub, or it's for accent lighting or something like that. So the picture there, created in Dialux on the lower side, it's okay if you're illuminating an event or something like that, where you're lighting round tables, for example. But if it was an office, of course, that's not very good practice. You're looking at good uniformity, and you can only do that with a luminaire that's got good photometry and that's suitable for giving you good uniformity. So, of course, the most expensive part of an LED fixture is, in fact, the LEDs. So if I can use fewer of them and gather the light up into a tight cone, the thing becomes cheaper. But that's not always best practice, because, of course, when you're looking at maybe lighting a corridor, say, if the beam angle goes from wide to very narrow, I'm doing it a lot more often in the design. So again, when you look at the overall system efficiency or actual useful building efficiency, the watts per meter squared per 100 lux for the application, if I need 3 times as many of these as I do of these, perhaps it's false economy, especially when you consider labour, other materials such as cabling, switchgear and so on. You know, a better design luminaire is going to create a lower watts per meter squared per 100 lux efficiency measure. So, what I want you to glean from this is the question to ask. Don't be fooled by manufacturers offering you products with very high lumens per watt figures. It could be, as you see on the left-hand side of the screen there, just the LED chip efficiency as opposed to the overall complete luminaire. Because when you take an LED, you've got to mount it onto a board, so therefore you get thermal losses. That might be 10 or 15% loss there. I've got to put an optic in front of it, as I've mentioned. That's going to be between another 10 and 30% loss. Then I've got to connect it to a driver, so I've got driver losses there, before I get overall system efficiency. So again, you should be asking in your schemes when you're comparing products like for like, what's the overall system efficiency of that product? Especially if you're maybe an architect or an interior designer or a building services engineer, and you're looking at comparing products. Maybe it's a tender that's gone out and it says equal and approved. You've designed it using a PhotonStar fixture. However, the fixture, you want to be able to compare that on a value engineering scheme, etc. It could be that you're comparing watts again, one 10 watt downlight to another 10 watt downlight. You can't do that. You've got to the unenviable task now of comparing so many other factors: overall system efficiency, beam angles, photometry, etc., longevity, warranties. So it is a bit of a nightmare. Make sure you know what you're being sold. Okay, quickly on understanding lifetime claims. If most LED products on the market have only been commercially released for about a couple of years, there's only 8,760 hours in a year. How do we know that the products are going to last the length of lifetime claimed in warranty? A lot of manufacturers now are offering up to 10 years warranty. How do we know that we're actually going to achieve that? Well, life of a luminaire is actually expressed, you may have heard of the term L70 for 50,000 hours. What we do is we measure the output of these fixtures for 6,000 hours, or if it's a lamp, 25% of the rated life. And we measure it at day one and measure the illuminance that's coming out of the fixture at day one. And then every 1,000 hours, we take it off test, remeasure it, and start to plot a degradation curve. We look and extrapolate that curve, and the point at which it crosses a point of 30% reduction or 70% of the initial brightness, that's what we class as life. And in the professional lighting market, it's true to say that 70% of initial light output is what we class as rated life. The product will actually go on operating happily, probably in excess of 100,000 hours, but LEDs don't just fail like a halogen lamp or a compact fluorescent lamp that might just switch off. LEDs just get gradually less bright over time. So they'll still operate. So if you build enough headroom into your lighting scheme, you can, of course, get a much greater length of life and therefore maintenance period. But the expression L70 50,000 hours means that the product would have reached a 30% degradation in light output against that when it was switched on. We categorise this as well because LEDs, as I say, they don't just fail, they just get gradually brighter with life. Some perform better than others. So when we're doing that test for 6,000 hours and we're mapping how much they degrade, we categorise them. So for those best performing that are furthest above the bar, they may have only dropped equal or less than 10%. So we class those as category 1, the very best performing fixtures and LEDs. Category 2 is a 20% loss, and category 3 is a 30% loss at that 6,000 hour point. I can say that this fixture that we keep using in the presentation, and indeed all other PhotonStar fixtures, are L70 category 1, so you're always buying the very best luminaire. So again, you can ask your LED suppliers, what category do they fall within their product? What do they fall within? Again, design of LED fixtures. If you look at the way that the electrical characteristics of the way that these LEDs operate, the harder you drive them, the shorter their life. So typically, if you can run an LED at 350 milliamps, even if the thermal ambient temperature is quite high, so if we can see here, 350 milliamp is the blue line. If you run it at 50 degrees C thermal ambient, you're going to achieve about a 75,000 hour life. If I run these twice as hard, which is what typically happens in a lamp, you'll get a 50% reduction in life output, half the life. So only 37,500 hours for one of these versus one of these run at 350 milliamp. So again, the fewer the luminaires, the fewer the LEDs in the luminaire, the harder you're going to have to drive them, the shorter the life. As a manufacturer, we don't know where our luminaires are going to end up. It could be all over the world. Therefore, we have to design our fixtures to operate in very high thermal ambience and still achieve that 30% light reduction within 50,000 hours. That's why we need a large heat sink. So it's true to say that all LED fixtures by PhotonStar are designed to give you the L70 50,000 hours, even at very high thermal ambience. So if we take this product, that's good to give you 50,000 hours L70, even at a thermal ambient of 55 degrees C, because I've got such a large heat sink on the back. All of our products are 45 to 55 degrees C thermal ambient rated, so very well designed indeed. So the key to it is ask certain questions for specification. At the end of the day, it's your professional indemnity insurance. If you don't know what you're buying, again, it's your company's reputation, your own reputation, and your PI at risk. So when you're appraising an LED manufacturer or a product, ask these questions. Now, these have been written by the Lighting Industry Liaison Group, the guide for specifying LED lighting. Initial luminaire lumen output at L100. L100 is just at day one, the initial brightness. Photometry at L100, is it available? The light output depreciation category, category 1, 2 or 3, is it one of the best performing ones, which is category 1, PhotonStar fixtures are. Luminaire life as a representation of the light depreciation at 50,000 hours, L70. 30% degradation for LED fixtures from PhotonStar at 50,000 hours. Failure fraction, color temperature L100, color rendering index value and any shift. And most importantly, the luminaire electrical characteristics, including power factor. Do ask that question. Pretty much every fixture from PhotonStar has a very, very good power factor correction. 1 being the best. You'll generally find that all drivers, etc., have certain losses in them. Our fixtures generally are 0.9 or above. I have seen products on the market that are lower than 0.5. So do ask that question. As I say, it's your PI. The Lighting Industry Liaison Group, you can go online. It's a collection of governing bodies such as the LIF, PEMSA, Society of Light and Lighting, ILP, the LIA, PLDA, and the ILD. They've got together to write these guides to help you guys out. you can go online or go in the back of that catalogue, find it on the PhotonStar website as well. Do ask those questions. They're there to help you as a specifier. I think that pretty much concludes the presentation. Sorry, if you do have any questions, feel free to email me direct. My email address is robert.tuck@photonstarled.com, robert.tuck, TUCK, @photonstarled.com. Thank you very much for listening, and I'll see you on the next seminar.